All right, party people. This is our lecture for April 30th, and this is our next to last new information lecture for the year. Wait a minute. How'd this get here? Oh, yeah. Well, that's important information. I want you guys to all know that. Of course, I'm just kidding. I want all the houses to do well tomorrow or today at the Griffin games, as long as at the end of the day Sapientia comes out on top. So, you guys play out the rest of that however you want to. Just kidding. All right. We want to do a quick review of 11.1, 11.2. Make sure that if you guys haven't watched that, I don't know why you wouldn't have, but make sure you do. There will be a lot of that stuff on the test. This is going to be probably a half vocab test because there's a lot of acids and bases vocabulary to absorb and be able to use in a meaningful way. Then pretty quickly we're going to move to 11.3. I think we're going to get through 1 and 2. I don't think we're going to get all the way through 11.3. There's a lot of information there. And I want to kind of wrap up and then go back over it on Thursday. Okay? Because then we will have a test, I think, next Tuesday, after which we will start our final exam review. And if you have not responded on the GroupMe, 7 of y'all, please do that and let me know that time's going to work for you, because if only 3 of y'all can do it and 7 of you can't, we need to find a different time. So, I think it would just be courteous to let me know that works. It's always good to RSVP to a party if you're invited. Not that it's a party. It will be as fun as a party, but I don't think we should call it that. Anyway, all right. So very quickly, flip back in your book. I'm not even going to try and get the camera working on it for right now. Remember that page 292, I suggest that you guys know the properties of acids and bases. So if you've got your book, it might be good to make little dots next to the paragraphs or sections that we're talking about so you know which ones to study and don't waste your time studying things that aren't going to show up. I think I do want you to know the scientific names, not the historical names, of the acids on 293. Those are very common acids, even in our day-to-day life, non-chemistry wise, just all over the place. So you do need to be able to answer hydrochloric, nitric, sulfuric, phosphoric, acetic acids, and all those properties of acids and bases there, including the ones that roll over onto 294, the properties of the bases. We talked about binary acids, hydrogen and one or more of the metals. Okay, so those are listed in a table there. Note that pattern, what makes something a binary acid. You'll probably be asked to identify whether something is a binary acid or not. Look at the oxyacids and what those include. I will not ask you to list any of those. There's not really any point in that. But I do want you to be able to recognize them. And then look at the carboxylic acids. They can contain the carboxyl group. Okay, COOH. And we see those listed right there in figure 11.4, acetic, formic, and benzoic acid. Okay, guys, you really need to be marking your chapters. Okay, you really need to be marking them. I see a lot of tests that if y'all just studied the right stuff, I know you could have gotten it right. Okay, so just make sure you're marking this as we go. I'll try to go over this again on Thursday just to make sure we're all clear. All right, flip over to 296. Arrhenius acids. You should have that definition underlined. Substance increases the concentration of hydrogen ions in an aqueous solution. And a base is the one that increases the OH ions. You see in the paragraph below mono, di, and triprotic. Make sure you know what those means. They donate what those mean. They donate 1, 2, and 3 protons to a solution. Pretty easy to identify. They usually have like an H sub 3 if they're tri, H sub 2 if they're di, and so on and so forth. Okay, you need to know that H3O plus is a hydronium. Okay, and we know that when those hydrogen atoms, those protons, end up in solution, we know that they basically get picked up by the nearest water molecule, and it, because of hydrogen bonding, ends up very close to it, and it ends up acting like an H3O plus ion. So there's not lone hydrogens floating around. Remember that they're picked up by a hydrogen. By a H2O and form H3O plus. Okay. All right. What else do we? All right. We talked at 298. Talk about what is a Bronston-Lowry acid, proton donor, and a Bronston-Lowry base is a proton acceptor. And remember, the major difference there is that this allows us to expand a little bit outside of specifically aqueous solutions, because sometimes acids and bases are not participating in water. Okay, so we can't form hydronium if there's no water to form that hydronium with them. Okay, so this lets us expand outside of water, but it is essentially the same thing. Note that in Bronston-Lowry, it's a proton donor. That's an H+. Okay? And in the Arrhenius, it wasn't helping to form an H3O+ by donating a proton into an aqueous solution. Okay? So again, they're not over and against one another, just that Bronston-Lowry is a little bit wider, a little bit more comprehensive of a definition. Okay? Keep going on 300, page 300. Okay. Let's make sure you are looking through figure 11.9 there, where it shows the acid, base, conjugate base. Note that the acid loses its proton and becomes a conjugate base. And where a base starts out, it gets a proton added to it and becomes a conjugate acid. You need to be able to label that. So an acid loses, you'll have a whole equation, okay, and a whole chemical reaction equation there, and you will need to basically make this diagram here where who's losing a proton, who's getting a proton added to them, who is the acid, loses a proton to become a conjugate base, who's a base, adds a proton to become a conjugate acid. Okay, and we saw on this table here, and I think I just said it, I'll sort of pick up our lecture right here because I think I sort of threw it in there at the end. But note what's going on in this table here. Make sure that we've got a good focus. Okay, there we go. All right, so these go in opposite orders. So for example, we have a strong acid. Note, what's the difference between these two? Lose a hydrogen. Okay, that's because this hydrogen pops off and goes into solution. Okay, that makes it a weak base. Okay, a weak base. And we see that this guy appears again down here. And he's still a pretty strong acid because it really wants to donate both of those. Okay, and so it still forms a pretty weak base. A little less weak because he's a little less strong. Okay, and we can think of that as kind of like the ionization energy, right? Like it's easy for that first hydrogen to pop off. A little less easy for that second hydrogen to pop off, but it usually does because it's mostly strong. Okay, and see how that ionizes 100%. So this goes to this 100% of the time, and this goes to that some lesser percentage. I don't know what it is. Okay, there's a equilibrium constant that tells us exactly what percentage goes into it. But the stronger the acid, the weaker the base, and so this base is a little bit stronger because it might pick up a hydrogen. Okay, it might pick up a hydrogen to go back this way, and therefore would be acting as a base. All right, and so now we've got really weak acid down here. It becomes a really strong, oh, I'm sorry, I'm off the camera here. Really weak acid here becomes a strong base. Okay, so OH is a pretty strong base. It is not going to donate another hydrogen. That's not going to happen. So it's going to be a really weak acid to do that, but a really strong base because it's going to really want to accept a hydrogen. Okay, and all this is to say, strong acids make weak conjugate bases, and strong bases make weak conjugate acids. Okay, they make the opposite strength once they become their conjugate there. Okay, that's what you need to know about that, and that will show up in probably just a sentence question where you're filling in the blanks. Okay, we're not calculating anything. We're not doing that. We just don't have the time to get into any of that. All right. Oh, and also page 302, you need to know what the definition of a Lewis acid is. Okay, so I would maybe make some note cards on that. Okay, and just want to show you guys this. I don't think I actually said this, but this is the, well, that's what I kind of paraphrased, but okay. That's where that was the actual book sentence of what I was just saying a minute ago. So make sure you get that noted there. You can read through any of this you want to see exactly what's going on math-wise there. Okay. All right. Let's jump into some new material. All right, so what we're going to talk about today is a phenomenon called the self-ionization of water. All right? Okay. What does that mean? Well, it means that just in the normal course of water being water, coming out of the tap, sitting in your glass, all right, some amount of those are hanging out as H2O, and we'll just call this 0, neutral. Some of them are hanging out as H+, and some concentration of them are hanging out as OH-. So we got some concentration of all of these. Okay, and remember that concentration for this chapter is moles per liter. Always. Okay? That's what our capital M means, molar. Okay, we're not fooling with molal, we're not fooling with grams per liter or any of that stuff. This is all moles per liter, molar, capital M. Okay? All right. So you can, for the purpose of this chapter at least, you can just put all that other stuff out of your mind. They're all useful in other contexts. They are not useful in concentrations of acids and bases. All right, and so you see right there on page 306, he's got this. And he just has it like this so that it balances. So we could have even just written that with 2 H2O. Okay. But this indicates that it's kind of going back and forth between the two states. Okay, that was one of the questions I asked you in the homework. Right, that's what that arrow means. It means it's not 100% zoom. This goes this way, and now those are our products. Okay, you pour it into the container, and it's already got this equilibrium figured out. So some of those molecules are becoming these, and some of these are becoming these in like a constant sort of, well, that's what equilibrium means, is that you've got things going in, things going out, but it's always staying right around the same number there. It's like if you were pumping into a container and pumping out of a container, the molecules of liquid in that container would always be changing, but the level in the container would be staying the same. Okay, so if in equals out, the level stays the same. That's an equilibrium situation. That's what we've got here. Okay, the question is, how many of these become how many of those? All right, and so we know, and I need to do some more reading on this before the next time I teach this class, for sure, okay? Because I always get into the details of these, and I realize I don't know, like, the next level of it. And I don't understand how exactly they got this constant. We just know it is, and I'm sure someone has rigorously proved it. That's bad science on my part, but, you know, I know physics a lot better than I know chemistry, and so I have a lot of learning to do in chemistry. So, but we know that, and remember, this means concentration when we write it in the brackets like that. All right, so note this equals OH minus, minus. Oh, well, he's actually got him inside. I'm sorry. Gosh, terrible. Doesn't matter. That's not the point. But we still got the H3O pluses, H3O minus equals 1.0 times 10 to the negative 7th moles equals 1.0 times 10 to the negative 7th moles per liter. Right? All right, so if I go in there and I pull out a liter of water, I will find in that liter of water 6.022 times 10 to the 23rd molecules of H3O plus ions in every liter of water. I will also find 6.022 times 10 to the 23rd molecules of OH minus in there. Okay? And I have just a curiosity. I don't know. Let's look at what percentage of it. Forget concentration here. Let's just do a little back of the napkin here. And this may not work out because I haven't worked this ahead of time. I should have, but I just thought of it. All right, so we know we've got that many moles per liter of both of these guys. So we got 1 mole of that floating around and 1 mole of this floating around. Right? So how many moles of water are just hanging out as H2O? All right, let's figure it out. So what? We got 1 liter is equal to 1,000 grams of water, more or less, given the temperature and the pressure and all that stuff. But we're just going to assume it's a nice even 1,000.000. All right, and so 1 mole of H2O is what? That's 2 plus 16 is equal to 18 grams per mole for H2O, right? All right, so 1 liter. Let's see, we want to get from liters to moles here. So we want to go Here we go. Yep. So we'll do 1,000 grams per 1 liter of water. And we'll do 18 grams per 1 mole. And what's that going to give us? So we just need to divide 1,000 by 18. My calculator has returned to me. It's been missing because it's been in my PE test taking box for a long time. Okay. All right. So 1 liter is 55 moles. Plus 55.56 moles of water. Okay. So total moles equals 55.56. Ionized moles equals 1 times 10 to the negative 7th. Okay, so this is not even like really a calculatable percentage, right? Because we've got 10 to the negative 7th divided by 55.56. So that's 2 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the negative 9th. Yeah, well, when we divide that, it's 10 to the negative 9th out of 1 there, so, or 2 times 10 to the negative 7% ionized. So a very, very small percentage ionizes, okay? Which we could have, I mean, we could have ballparked that, right? Because it was 10 to the negative 7th. But I was curious how many actually moles, how big of a number that would even make it. So it's like let's say, so a billionth is 10 to the negative 6th. I'm sorry, that's a millionth. A billionth is 10 to the negative 9th. So so basically 1 billionth of the ions of the H2O molecules become ions. Okay? Not that any of y'all cared about that, but now my curiosity has been satisfied. So thank you for bearing with me, and go Owls. Okay, so all right, so those are our concentrations right there. Okay, and so we have this Kw, this ionization constant, which you don't need to know anything about other than, okay. And again, some of what we're doing is just preparing you guys for when you see this later in your life, you won't be totally confused. Okay? So this constant is just the multiplication product of these two concentrations. And we said that this was 1 times 10 to the negative 7th. And this was also 1 times 10 to the negative 7th. And that becomes 10 to the negative 14th. Okay, 1 times 10 to the negative 14th. Okay? That's it. Okay, so this is our equilibrium constant. All right, and so this is for pure water. This number exists for all sorts of different, so if something does not ionize completely, we need to know how much it ionizes. That's what the equilibrium constant tells us. Okay, so in our case here, it's very, very small. Sometimes they're a lot bigger than that. Okay, they might be 10 to the negative 5th. Okay, but again, without doing a whole lot of work to really get into that, it's hard to get you guys, familiar with it and able to work with it. So right now we're just sticking with kind of the basic concept here is that we've got these two concentrations you multiply them together to get the constant. Okay, so if I ask you to solve for the equilibrium constant for something, all you got to do is multiply the two things together. Okay, and remember that this is molar, right? So we know that's what kW is. He says that at the middle of 306. Our purposes, you may assume that any ordinary laboratory temperature, it's equal to 1 times 10 to the negative fourth m squared. All right, so now we're going to move into a little different situation. Very quickly, going to work through example 11.3. Okay. Let's see. Yeah, let's just do that. That's good because that's the kind of question we can then ask on a test once we've worked through it like this. Okay. All right. We have CaOH2. Crooked here. All right. Disassociates completely, and we want to know the H3O plus and the OH minus of a 0.0012 molar solution of calcium hydroxide. Okay, so what happens? So this goes to a Ca plus and 2 OH minuses, right? Because there's two of them right here. It says it disassociates completely. The whole thing comes apart. Okay. So for if it was 0.0012 molar, we want to know what's it giving? It's not giving any hydrogen because that hydroxide hangs out as a unit. Okay. So it's giving these hydroxides. Okay. So we have 0.0012. And that makes a 0.0024 molar concentration of the hydroxides. There are two of them. You put 0.0012 moles per liter in there. It's going to create 0.0024 moles per liter. Okay? And now we use the ionization constant of water, H3O plus times OH minus equals 1 times 10 to the negative 14th. Okay, so this is an important number to know. Okay, and so now, because we're looking for the two concentrations, we've already solved for this one. Okay, because it told us that's what it was. All right, and then we need to solve for the other one, because when one of these becomes this, the hydrogen follows suit. Or if we donate a bunch of hydrogen, the hydroxide follows suit. So if we say H3O plus times, what's our concentration? 0.0024 molar equals 1 times 10 to the negative 14th. Divide both sides. And our H3O plus is equal to, he solved it for us there, 4.2 times 10 to the negative 12th molar. Okay? Straightforward. That 1 times 10 to the negative 14th is only for water. And so anytime we're talking about ionization constants, you need to make sure it's in water. We're not doing anything other than water, so that will be your ionization constant. Okay, and it basically just lets you plug in and solve for the other ion concentration once you're given one of them. Okay, and note that it's a 0.0012 molar solution, and so it's already in solution. It's already aqueous. All right, now let's move on to the next little thing here. This is 11.3.3. pH is equal to the negative log of the H plus. pOH is equal to the negative log of the OH minus. Okay. And I'm just going to write these and then we're going to explain them. pOH is always equal to 14. So these are all things that you saw briefly in that video, okay, of the crazy fast talking dude from YouTube. Okay, but now we're going to really hit them and be rigorous with them here. And this, I'm sorry, I really should have written H3O plus here. Sorry. Okay, those are the same deal, right? All right, and then yeah, okay. So we're just gonna leave it with those. Okay, so very, sort of very straightforwardly here. Let's just take this right here, and we say, so what's the pH? Well, literally all you do is you say it's equal to the negative log of 4.2 times 10 to the negative 12th. Okay, so we would say negative log, and it opens the parentheses for you. 4.2 times 10 to the negative 12th. Close those parentheses, close the overall parentheses. Boom. Was 11.4. Okay? So what does that mean? Okay? Well, if you look right here, I think you guys learned this, years ago, but we know that 7 is exactly neutral. Okay? Anything below that is an acid. There will be some questions on just, hey, this thing's got a pH of 5. Is it an acid or a base? How do you know? Okay? Anything over 7 is a base. It's basic. Okay, and you see the list of things here. There's for years I would have sworn that milk was a base. It is not, apparently. It's actually very close to neutral. I don't know why I thought it was a base for years and years. So anything that's sort of tart, sour, generally going to be acidic. Okay, note these foods that are. Have you ever had a paper cut, or if you're like me and you get sort of canker sores in your mouth? These are super unpleasant. Okay, you ever got a cut on your finger? You don't want to get anywhere near tomatoes, lemon juice, vinegar. They will make it burn in a heartbeat. Milk doesn't really bother much because it's pretty close to neutral. And then you got these pretty strong bases down here. Okay, you don't want to fool with these either, because they will tear your skin up with a chemical burn, just like an acid will. Okay, but back to our numbers here. So let's look over here with this. Okay, so all we did was plug this into the calculator. Okay, and what he's got going on here is that if we know, if you look at the top of 11 there, let's say we have something, just a nice even number without that decimal number in front of it right there. So this would be a 1 times 10 to the negative 5th. And we take the negative log of it. It's going to be equal to 5. Okay, it's pretty, you can verify that. Negative log 10 5th. 5 exactly. Okay, why is that? Well, it should tip you off that these are on the same key right here. Okay, 10 to the x and log, because they're the inverse of one another. They're inverse functions. All right. So like he's got right there, log of x is equal to y. 10 to the y is equal to x. And of course, this is have a understood base 10 under there. Okay. So it makes sense if I'm asking log of something right here. Basically, what happens is this gets pulled down. Okay, whatever the exponent is gets pulled down. All right. So why doesn't this get pulled down? Well, because it's not right. It's not right on 10 to the negative 12th or 10 to the negative 11th. Okay. But what you can know is that this is on its way. See, like if this was 10 times 10 to the negative 12th, it would actually be 10 to the negative 11th. Okay. So you know this number's on its way to being 10 to the negative 11th. So it's somewhere between 10 to the negative 11th and 10 to the negative 12th. Well, 10 to the negative 11th is a pH of 11. 10 to the negative 12 is a pH of 12. Okay, so you know it's going to be between 11 and 12. All right? And you have to do a lot more of these to where you were comfortable sort of like getting a sense of it. Okay? But let's go back to this one, okay? So this is the way it always works. All right, so if we know the pH is 11.4, what's the pOH? Well, if we know pH plus pOH is equal to 14, and pH is 11.4, pOH is what? 2.6. Okay, it didn't change from an acid to a base. We're just labeling it differently. It's still got a pH of 11.4. It's still an acid. I mean, it's still a base. Okay, but now we're going into here, and we're saying, oh, look, we know they're going to add up to 14, so we have another way to write it. Well, what does that help us do? Well, that helps us get to. Well, now if I asked you what's the concentration of OH minus, what would we do? All we'd have to do is we'd have to say 1 times 10 to the negative 2.6. Okay, you take this number, put it negative above the 10. pH was 5. We take a negative of it and put it above the 10. Okay, so what would we do with that now? We could say 10 to the negative 2.6, and we could properly write it as what? 2.5 times 10, 1, 2, 3 to the negative third. Okay, so what? Sorry. All right, so what are those steps? Okay, if we're given an H3O plus, we're given the concentration. We can plug in a negative log of that number, pull it in, gives us a pH. We can go from pH to pOH by subtracting it from 14. Once we've got this, we can take 10 to the negative 2.6, plug it into our calculator, and we can get a properly scientifically notated answer of this. Okay. Also, we know another relationship that lets us go straight from here to here. Okay, so if we didn't care about the pH and the pOH, and we just said, all right, here's our concentration here, what's our concentration here? We could do it very easily because we know that H3O plus times OH minus is equal to 1 times 10 to the negative 14th. So now we plug in. We say 4.2 times 10 to the negative 12. This is what we're looking for. Okay, so we would then say, my lighting's bad here. All right, so what would we have? We'd have 10 to the negative 14 divided by make sure you open your parentheses, 4.2, and you can, this little e is the shortcut for times 10 to the. Okay, so we could actually do this. 1e to the negative 14 divided by that. Okay, and what do we get? 2.38 with a little rounding error here. Okay, so same answer, right? This is, we'll say it's about equal to that because we rounded off on our pH pretty solidly there, because we got so we rounded that, this 11.37 here. So that's what accounts for this discrepancy here. Okay, so this is something you need to be familiar with. I recommend rework on your own. Okay, follow it, replay this video, do whatever you need to do. Okay, don't get so hung up in the math that you don't understand what's going on, but don't just think, hey, all I need to know is they add up to 14. Okay, you need to be able to work with some of this. Okay, and let me know between now and Thursday if we need to go back through this. I will be glad to spend time going back through this again, because this is some basic stuff that will be very useful for you to do on your test. So you need to familiarize yourself with it. I will give you some homework for this. All right, and then I will make sure I get you the worked out solutions to those over the weekend. Once you have, let's see, Tuesday. Yep, so it'll be due Thursday. Okay, and then I will get them to you Thursday or Friday, the worked out solutions, and then you can go through and work them and be ready to review them. You'll be ready to take the test on Tuesday is what we'll do. Okay, and then let's see, we're kind of running out of time here, probably. Let's we'll hold off on that. If you guys want to go ahead and you have time, work through 11.5 because it's reiterating what we're doing. And if y'all don't get it, I'll let Miss Barron tell me that, and I will try to work it out on Thursday. Okay, well that sounds good. Keep plugging away on revising your lab reports. I think I sent out a date on that, but I will check, and if not, I will send out a date on that. Maybe I'm feeling like it was May 7th, but I'm not sure now. That was before the weekend. So, all right, good deal. This is not super scary, even though it's got a lot of parentheses and powers and all that stuff. You just need to work through what's going on. Take it slow. Take some time. Get it from the screen into your brain so that you can work with it. And I will make sure that the homework reflects what I need you guys to be able to do. Okay? Alrighty. Well, I'll talk to you soon. Let me know what you need. Shoot me an email if you need anything. Okay? All right, bye.